So good evening, everyone. So I just start by recalling Barlecum's algorithm, which we have seen last time. I mean, just yesterday. Uh, so, uh, so this is the factorization algorithm which we were discussing. So fx is a monic polynomial, monic square free polynomial. So square of no polynomial divides it. So it's not divisible by square of any polynomial. It's uh, okay. I should also put my video on. Yeah. So it's a monic square free polynomial with coefficients from a finite field fq, and we would be using only prime fields with p elements, where p is a prime. So prime powers we are not going to use because of the complications in implementing on the software. The algorithm works for any finite field. So square free polynomial in. So we would just stick to f p of x, where p is prime. So I just simply recall the steps. So step one uh, is to look at the okay, suppose the degree of this, we need to check the degree of fx. So suppose degree of fx is n. Then we look at these powers x to the I p. P is the p of the finite field, and reduce it modulo fx. Let me write it like this. So for 0 less than equal to I less than equal to n minus 1. So I is running from 0 to n minus 1. We reduce x to the IP modulo fx, the polynomial we started with, and write that in this way, that bij x to the j is running from 0 to n minus 1. So this is going to be when we reduce modulo, sorry, mod fx. So when we look at this polynomial congruence, we reduce it modulo fx. So fx being a polynomial of degree n, so this representative is going to be of degree at most n minus 1. At most n minus 1, it need not be n minus 1. Of course, the coefficients can be 0. Many other coefficients will be 0 in fact. And then we construct this matrix with these entries bij. So this is an n cross n minus, sorry, this is n cross n matrix, n cross n matrix over f. So entries are from the finite field. They are just coefficients of this reduced polynomial. Step 2 would be to look at the rank of this, rank of b minus I. So suppose that is R, then let k equal to n minus R. So this is also the dimension of the null space. Null space of B minus I. I is the n cross n identity matrix. B minus I. And if k is 1, that is the rank is n minus 1, then f is irreducible. Irreducible. And we stop. Irreducible, and we stop. So we stop. So if the dimension of the null space is greater than equal to 2, then we proceed. So we go to step 3. So if k, which is n minus the rank, and that is same as the dimension of the null space. So if that is greater than equal to 2, then we write, okay, no, let me write it in this way. So if this is if k is greater than equal to 2, the dimension of the null space is greater than equal to 2, then we proceed. So proceed in this way. So we observe that we actually have seen that yesterday, that this vector 1 0 0, this n minus 1 zeros, preceded by this 1, this belongs to the null space. So this is in the null space of B minus I. So this is in the null space, and we construct a basis for the null space starting with this. K is the dimension, so we get k basis vectors. So we construct basis of null space of B minus I. So suppose the basis vectors are C1 bar, and so C1 bar, C2 bar, and CK bar, where the first one is the vector we started with. So where this C1 bar is this one, that 1 0 0. So n minus 1 zeros following 1. So suppose this Cj bar is a, so it's an in length vector, and let's write it as C0j, C1j, C n minus 1j. So if we write it in this way, let me just add a page. Just so if this is the jth vector, uh, so j is from, so for yeah, so also from for the first vector, 1 less than equal to j less than equal to k. So then we write down these polynomials hx, whose coefficients are coming from here. So C0j is the constant term, C1jx, C1jx, and C2jx squared, plus so on so forth x to the, so c n minus 1 j x to the n minus 1. So we write down this polynomial. And what we have seen yesterday is that these polynomials uh, are f reducing, except for the first one. First one is a trivial polynomial, it's just one, because this the for j equal to 1 we get just these vectors, so that's a constant polynomial, namely just 1. And all others work as f reducing polynomials. So h2 of x to all of them are f reducing. So these are f reducing polynomials. So are f reducing f reducing. So they are all f reducing. So what do we mean by f reducing? We have seen that this is always true, that f can be written as a product of GCD of fx and hx minus c for any polynomial h, and this is c running over the field. So we have seen this equality, we have proved this equality, so this is always possible. And a polynomial hx is f reducing if this offers a non-trivial factorization. So non-trivial factorization of fx. So by non-trivial factorization, I mean that no factor is fx. So it can be just fx into 1. So that is a trivial factorization. So non-trivial factorization is just avoids that. So none of the factor is equal to fx. These factors need not be irreducible. Factors need not be irreducible. This is just a non-trivial factorization. It's not factoring into irreducible polynomials. But what happens in this algorithm, that we do this with these polynomials. So this with this j. So we try this with these polynomials, and if we keep doing it using one polynomial, then whatever factor we get, we use the second polynomial to factorize that, and we keep doing it. Then we have seen that this algorithm separates all irreducible factors. So finally, we would be getting fx factored into irreducible factors. So we start with h2, and then whatever factor we get, uh, we we do the same process with h3 and so on. So let's just work out examples so that we know what we are talking about. So the first polynomial, I have worked it out already. So I would choose that. So we start with that, and then you can just suggest me a polynomial. I'll try that. So entering the matrix will take time, otherwise the other steps are very fast. So just let me write out a polynomial. So let's work out this example. So the example we are trying first is fx equal to x to the 8 plus x to the 7, x to the 4, 8, 7, 4, x to the 3, x to the 8, x to the 7, x to the 4, x to the 3, x plus 1. So anything works, but I have just worked this out. So let's start with that. Then we would do an arbitrary one. This is a polynomial on f3 of x. Yeah. So I'll start with that. So let me just open the program and start writing. So can you see the browser?
Yes.
Okay,
Yes,
okay,
there is.
fine, thank you. So I'll just start. So first of all, we have to define the polynomial ring we are working on. So that is written in this fashion. So just let me write this polynomial ring GF3. So GF3 is just a command for F3. So if this is a finite field with three elements, and I can give a name to the variable, so which is the x. We are choosing x. So that's the entry. So R is so I just defined the polynomial ring, which is R, and with the variable x, and it's over GF3. So which is F3. So let's say that. So this says that univariate polynomial ring in X over finite field of size 3, and that is what we want. Now let's write out the polynomial. So sorry, I just write small x. Small x equal to uh, x to the 8 plus x to the 7 plus x to the 4 plus 8 7 4 x to the 3 plus x plus 1, x to the 8, x to the 7, x to the 4, x to the 3, x plus 1. Yes. So let's see if we entered it correctly. Yes, so that's the polynomial. Uh, yeah. So let's work it out. So the first step is to find the congruences. So now the degree of the polynomial is 8, and we have to and p is 3. So we have to look at x power 3 9 sorry 3 6 9, all these multiples of 3 till 24. So we do that, sorry, till 21, because it's n minus 1. So degree is 8, so we need to multiply 3 by up to 7. So up to 7th multiple of 3. So a 0th multiple, we don't need to do anything, because the 0th multiple is x to the 0 is just 1, and if we reduce it modulo f, then it is just 1. So that's the first entry. In fact, that's the reason we have this 1 as followed by 0 as the first as an element, as a vector in the null space. So that is the reason. So we start with x. In fact, all these things till the power of fx would just give the same thing. So if you reduce modulo f, it you get the same thing. So the reduction command is this percentage f. So this is obviously because it's the power of x is less than the power of the degree of the polynomial, you will get back the same thing. So it's, just to list it, so doing it just one more such thing. If so, that is of course the same. now the things will change. We would go to 9 and which f, so 9, so that gives a, so this is the residue when reduced modulo f. So now some coefficients have started coming. So this is 9, 12. So all multiples of 3 till we reach 21. So 12, then 15, 18, 15, 18, 21, 21. Yes, so that's the last one. So we have all these reductions, and the coefficients of these polynomials would give us the matrix B. So thing is that the entering the matrix would be is quite long. So I would just copy paste from my working, which I have done earlier. Let me try. I can just get that. So, so I would simply copy paste the matrix from here if it works. It's very long, so yeah, it works. So this is just entering the vectors. So I would explain how I entered. So yeah, so these things. So when I reduce in fact x to the 0, then of course this is the first vector one. It should be 1 followed by zeros, or zeros, and then x to the x cube reduced is also x cube. So this entry is at this fourth place. We have 1, because this corresponds to the 0th power, the 0th the constant term, then the first power x square, x cubed, x4, x to the 4, x to the 5, x to the 6, and x to the 7. So next one is x to the 6. So we have an 1 here and 0 everywhere else. So this corresponds to the x to the 6th power. Then if you look at this, the x to the 9, when reduced modulo f, it is x to the 7, x to the 7. So last entry should be 1, and there is no x to the 6, so that is 0. The next one is x to the 5, so it is 2x to the 5, which gives a 2 here, and followed by a 0. There is no x to the no entry for x to the 4. X to the cube has coefficient 1, x square has coefficient 2, x has coefficient 0, and 1 is 1. So it has a constant term, so that is 1. So likewise I entered, sorry, so likewise I entered the whole so all these entries ending with let's check that. So this is the last one. So this is x to the 5, x to the x square, and plus 2. So x to the 5 has coefficient 1, and then x square and constant term. So this is the matrix. This is the matrix. Let me just write down the matrix. Sorry. Let's just see the matrix again as in matrix form. Yeah. So it gives you the matrix. So it gives you the matrix, and now we want to subtract the identity matrix from this. So let's define I to be the identity matrix. So I equal to identity matrix. So this is 8 cross 8. So identity matrix 8. And let's see how it looks. So this is I. Yes. So we have this identity matrix. The next step is to subtract that. So let's give it a name. Call it C. So C is B minus B minus I C. So we subtracted. So C is the matrix we subtracted. And so of course the first row has become all zero because the first row of B and first row of the identity matrix are exactly same. So that has become all zero. Now we can check the rank by reducing it to echelon form, row echelon form. So let us do that as well. In fact, finding the just looking for the null space is fine enough. You don't have to do this step. But since we have small entries, these things are calculated very fast. So let's see that as well. So that is done. And then obviously the rank is 5. And so dimension of the null space is going to be 3. So we have, so F is going to have 3 irreducible factors. So as soon as we find 3 factors, they have to be irreducible. So now let's define this null space, just calling it NS for null space. So that is this is how it is defined. So it's called kernel in this program. So kernel of this matrix C is B minus I. So now what is NS? So it says that there's a vector space of degree 8. So it has eight variables. So it's a subspace of 8-dimensional space of dimension 3 over finite field of size 3. And it gives the basis vectors, and the first one is that the one we are always writing down, so that vector. So we have two non-trivial vectors. So first one is of no use, and we have two non-trivial basis vectors. Therefore we can now construct uh, two non-trivial f reducing polynomials. So we'll do that. So we construct this H2. So H1 is corresponding to the first basis vector, which is just the constant polynomial 1. We don't use that. So start with H2. So let me just write that down. Uh, so yes, so this is the polynomial corresponding to the second entry, second basis vector. So it doesn't have a constant term. Constant term is 0. It starts with x plus x squared plus no cube term. Then 2 is the coefficient of fourth power. 2 is the coefficient of fourth power. 2 is again coefficient of fifth power and sixth power. So they are same. Fifth power, so to sixth power. So fourth power, fifth, yeah, fourth power, fifth power, sixth power all have coefficient 2. So 2, 2, and 2. And seventh power comes with coefficient 1. So just takes to the 7. Let's see, it looks fine. So yeah. So x to the 7, 2x square, x to the 6, 2x to the 5, 2x to the 4, and x square plus x. So that's our first polynomial. And let's also write out the second one. So h3 is smaller. That has only two entries. So x to the 7 and x cubed. So x cubed, sorry, plus x to the 7. Yeah. So x to the 7 plus x to x cubed. Now we want to find the GCDs. So GCD of f comma first of all is h2. So that is x plus 2. So we already have a non-trivial factor. GCD of f comma h2 minus 1. We have another factor. So GCD of so we need three factors. We are going to have three factors. So I mean, as soon as we have three factors, they have to be irreducible. So this is f comma h2 minus 2. So these are GCDs of h2 minus the elements of minus c, so which where c runs over the finite field. So we have three choices, 0, 1 and 2. So 0 is the first one we did, and then h2 minus 1 and h2 minus 2, and that's also, but this GCD is 1. Let's calculate with the okay, so yeah, so this GCD is 1. Now the first GCD, so GCD of f and h2 is x plus 2. So that is certainly irreducible because it's a linear polynomial, it cannot be reduced further. So this one needs to be reduced. So we can do it with the second one. So let's give it a name to say G1. So G1 is equal to this GCD. So GCD. So now we don't have to work with f. We have already separated a factor of f, and this is a non-trivial. So f is now product of this and this, and of course also this, but this is just one. So f is equal to this into this, and this being irreducible, we just have to bother about factoring this part. So the second factor, and let's give it a new name, GCD of f comma h2 minus 1. So that is just giving it a name. Let me see if we have entered things correctly. So yes, so we get the same thing. So just checking that. So G1 is this new polynomial which we want to factorize, and we would use H3 as the reducing polynomial. So now again calculate GCD, but this time not with f but with G1. So G1 H3. Let's see what it gives. So it gives 1, no use. So GCD of uh, G1 comma H3 minus 1, that gives another factor which is certainly irreducible. It is x plus 1, a linear factor. So GCD of h3 minus 2, sorry, so I didn't write this polynomial at all. So GCD of G1 comma h3 minus 2, yes, so that gives another factor. So these three, the product of these three is G1. So G1 is product of these three, and this is an irreducible factor. So we have, for x we have these irreducible factors. So initially when we tried with this f reducing polynomial h2, we could factorize f as product of this and this. And then this is of course irreducible being linear, so we started with the second one, we called it g1, and now g1 is factored into these two. So therefore, uh, if I write out this, so x, so let me just write it, x plus so what so just gathering the results, so we got x plus 1, x plus 2, x plus 2, and then we have x plus 1. So x plus 2 into g1, and g1 is factored into uh, x plus 1, and then we have this. Let me write that as well. So this to the 6 plus x to the 5 plus x to the 4 plus x to the 3 plus 2 x squared plus 2x plus 2. So just trying to write this. So x to the 6, x to the 5, x to the 4, x to the cube, uh, 2x 2x square, and 2x plus 2. Yes. Minus ff. So minus f, and then what do we see? Yes. Okay, so no, there is a mistake. So some mistake somewhere. Where did I mistake? Yeah, one second. I just. Oh, sorry. This is a. X minus 1. Hmm, x to the 6, x to the 5, x to the 4, x cube, 2x square. Hmm, six. Hmm, okay. No, there is something wrong here because I think why it is wrong, because the constant term here is 2 into 1 into 2, which is 4. So when reduced over f3, it should have been 1. So this is not a correct result. So there is some and of course the degree. So okay, so okay, sorry, this the problem is that I didn't put a star here, I think yeah. So yes, so it did not even multiply, sorry. Yeah, so it did not multiply, yes. So this is f. So if you subtract f, yes, so it did not multiply, yes, so you should be getting 0. So you should be getting 0. Now we have factored x into 3 factors, and that they have to be irreducible. Of course, the first two factors are irreducible because being linear, but once we factor into 3 factors, it has to be, all of them have to be irreducible, because we know from our theory that f has to have 3 factors, because the null space of b minus 1 has dimension 3. So that's how it works. uh, it gives factorization of now it's your turn to choose a polynomial, and I will try this. So can you just suggest me a polynomial? So just suggest any polynomial. So slightly smaller degree, so smaller number of term is better, but it's okay. So I mean, don't go past 8. So otherwise, the putting the entries in the matrix will take a lot of time. Otherwise, it's all fine. So just please suggest a polynomial. So anyone want to suggest a polynomial which we would like to see factored so for any field, any finite field. Okay, so I would also like to, when we calculated, I would also like to tell you something. So when we are calculating the GCD, so we have calculated certain GCDs which are 1. In fact, if we look over a finite field, if we look at polynomials over finite fields where P is quite large, so finite field with many elements. Here we just have 3-element finite field. So if we have a bigger finite field, then what will happen? Many of the GCDs are going to be 1. But the program takes a lot of time to calculate the GCD. So that is wasteful. So it is a good idea. In fact, I can tell you from here. So, so since you are using this, that fx is factored as product of GCD of fx and this hx minus c. So if you can characterize the C, characterize the elements of the finite field such that the GCD is 1 and then avoid them, product, that will save a lot of computing time. And that is what is done in more efficient algorithms. So this is the basic one. And if you and this but this works fine for small finite field. If you want to do it on a large finite field, then this algorithm needs to be modified. So those modifications are all available, but this is the basic algorithm. So all the modifications are based on this initial algorithm provided by Barlican. Okay, so any polynomial, would you like to suggest a polynomial?
Uh,
Yes.
so x power 9
X power 9. Okay. So I just modify this x power 9. So what is your finite field? Just let
f
me modify.
f of 9, sir.
No, so there is a yeah. So I should have told you that. So there is a problem in going to this prime powers because this program how it implements this finite fields of uh, higher degree by looking at the polynomial ring. So if you look at this say GF9. So if you want to look at GF9, then what it would do, it would write it down as F3 of X quotiented by an ideal generated by a polynomial of irreducible polynomial of degree 3. So the elements of that uh, would be polynomials. So they would be reduced polynomials. And then if we want to look at the polynomial ring, so that will be polynomials in 2 variables, and that's pretty complicated. So just choose a prime. So so what about 5 then? Since we have already done 3. So shall we try 5?
Okay, sir.
Yeah. So I'll try.
Okay, sir.
Yeah. So just finite field of size 5. And so just tell me your polynomial. So if to the 9, sorry, x to the 9, then
And 4x power 6, 4
4x
into
power
x power
6.
6,
Yeah. So 4 into x power 6,
3 into x power 4,
3 into x power 4. Okay, yeah, x power 4, yes.
plus 3x power 3,
3x power 3
plus x.
plus x plus and constant term.
No, sir. Constant term.
No, I mean, no
0
point in,
constant.
yeah, so if you do not give constant term, then of course x is a factor, so we can take that out.
But,
So better to put a constant term.
okay.
So constant term can be
4,
anything
sir.
between
4.
4. Okay, fine. 4, fine. So let's see if we have entered it correctly. X to the 9, 4, x to the 6, 3x to the 4, then 3x cubed plus x plus 4. Yeah. So now we have to look at powers of 5. So x 5. So that is obviously x5. So there is no, so then but I just kept it. And then next power is 10, x to the 10, reducing it by modulo f. So we reduced, then the x to the 15, x to the 20, 20. Yes, we are going to get a large matrix. So 25. So degree is 9. So we have to go up to 8 multiples of 5, which is 40. So 25, 30, 35. Yes. So we need one more. So I would just add one. How does one? I think I can add a cell here. I just, yeah, just add a cell here. So did I cover all the powers? So first power. So x to the 5, x to the 0. Start from x to the 0, x to the 0, x to the 5, then x to the 10, 15, 20, 25, 30, 35, and 40. That's the last power. So x to the 40, f. Yes. So we have everything. Now the difficult job is to give the matrix entries. Let's do that carefully. That requires doing it carefully. Other steps are really, so now we are on GF5. So first vector remains the same but increases in length. So it is now in now we are looking at a 9 cross 9 matrix, 9 being the degree of f. Second entry is x to the 5. So that is only at fifth power. So zeroth power, first power, second power, third power is also 0, fourth power, and fifth power. So in one here. So and sixth power, seventh power, eighth power, all are 0. Yes. So and then we have x to the 10. So x to the 10 starts with x to the 7. So 7 is this entry. So the last power is 8. So 9-degree polynomial. So 8. So here it is 1. Then nothing in sixth power. Yeah. So yeah, so seventh power. Uh, so I'm just writing this x to the 10. So this nothing in sixth power. So fifth power is 2, coefficient 2. Fifth power also has coefficient 2. Maybe just put a 2 here, which need an extra 2, extra vector. So extra entry. So it's a 9 length vector now. So 0, 1, then fifth power. Uh, fifth power is 2. Fifth power, fourth power is also 2. Then third power, second power is 4. Second power is 4. And then first power is 1. First power is 1 and 0. So hope it is correct. Then we go to the next one. So next one also starts from, so I put an extra 0. So the last power is 0. Eighth power is 0. Seventh power is 3. 3. Uh, then sixth power is 1. Fifth power is 4. No, I made a mistake, I think. So 8, 8, 7, 6. 8 is 0. So 7, 6, 5, 4. So 7, 7, 6, 5. Then another 4. 4. Uh, that is fourth power. Third power is 2. Third power is 2. Second power is 3. Second power is 3. Second power is 3. First power is 4. And 3 for the constant. Yes. Okay, so it has every term, in fact, x square, x cubed, x4, x5, x6, x7, except the highest. Next one comes with the highest power. So I just start by putting an 1 here. So I'm writing now x to the 20. So that is the first coefficient. Yeah, first coefficient is 3, not 1. So that is 3. Then again 3, 3, 3. Then 4, 4, 3. So 8, 7, 6, 5, 6, 5, 4, 3, 3, 6, 5, 6, 3, 3, 4, 3, 4. So 3, 3, 4, 3, 4. And fourth power. Then third, second. Oh, so it has every power. So then that makes it easy. So just 1, 1, 2, 2, 2. So 2, 2. So let me just see that again. So that is 2. So from the beginning, it should be 2, 2, 2. Then 2, 2, 2, 1, 4, 3, 1, 4, 3, and 4, 3, 3. So yeah, it seems correct. Then we have the next one, the slightly shorter now. So that is x to the 25. Start with a 1. So first entry is 1. Second entry is 0. Second entry is 0. X to the 7 doesn't appear. X to the 6 has 3. X to the 6 has 3. X to the 5 has 4. So x to the 5 has 4. uh, sorry, 25. So this is 103 from the highest power, 103, uh, 41, 41, 103, 103, 4, 1, then so 334, 3, 3, 4, 2. Let me just check. So 2 4 2433. So 2433 1 1414301. So that's correct. Close to the, then the next one is 30th power. Yeah, next one is 30th power. 30th power starts with a 3, then 0. Good, that is 1. Sixth power is 1. Then fifth, fourth, third, second, first, every power is there. So we have 1. Then 2 3 4 3 4 1. So 2 3 4 3 4 1. Let me just check. So from the other direction, so it is 1 4 1 4 3 4 3 2 1 4 3 4 3 2 143432 come here. So then I have 103, 103. So that looks correct. Next one, that is 35. So that has 7 8. So first three powers are 1 4 and 4. So 144, we just enter 144. So 1 4 4. So 144. Then the fifth power is 0. Fifth power is 0. Fourth power is a 4. And so that is 35. So x to the 35. So that is 4. Then I 0. Then is 0. No third power. Then 1, 2, 3. So then it is 1, 2, 3. So let me just check that. So 3 2 1. So 3 2 1 from the other direction. So 3 2 1 from smaller power to larger. So 3 2 1. Then I have 0 3 2 1 0. Then 4 4. Sorry, 404. It should be 404 3 3 1 0 404 404 4 1. So 40441 441. So because it has eighth power, seventh power, sixth power. So highest power is there. So yes, so one more entry. So we are now at 9 cross 9. The example we just are modifying is 8 cross 8. So we have one more entry. So that let's start from the constant terms. So this is 3 comma 3 comma 3. So 3 3 3. Then again 1 comma 1. So that is 3 3. First power, second power, third power is 1, fourth power is 0, comma 0. So fourth power is 0, fifth power is 2, fifth power is 2, sixth power is 1, seventh power is 2, eighth power is 1. So let me check that. So the missing power is only 8765. 4 is missing power, then 3, 2, 1. So only one is, so only 1 0 in that vector. Oh, I just put too many commas. Yes, yes. So this should look like 3331. So 3331, then a 0, then 2121. So 2121. So hope we have correctly entered this. Let's try. Yes, so at least yes. So we have the matrix 9 cross 9 now. So identity matrix needs to be changed to 9. So let me this all these remains same. Yes. So we are going to have two factors, because this is the null space is going to have dimension 2. So we have two factors. So let's look at that. So we have only h2. Let's quickly write it. We're going out of time. So x 2x square, 2x square, uh, 2x square, then x cubed. So h3, just writing the polynomial corresponding to the second vector. First vector is of no use for us. So it's just constant polynomial 1. So this is this corresponds to x. So x has coefficient 1, x square has coefficient 2, x cubed, then 4x to the 4, 4x to the 4, 3x cubed, 2x to the 6, 2x to the 6, and 4x to the 7, plus 3x to the 8. Huge. So 3x to the 8. Let's see if we have entered it correctly. So the 3/4 of the coefficients should be so all terms are present except the constant term, and the coefficient should be 3423. So 3423, 4121. So 4121, that's correct. uh, we don't have any others, so that is, we don't need that. So we just directly, we just delete this. One second, just delete this next column. So GCD, we have to look at GCD. Oh, very surprising thing. So it gives the same x plus 2. 2. So we don't need to do all this. So we just delete some of the cells, the earlier ones. So let me just delete them. Okay, we'll check there. So instead just add a few cells. So then GCD H2 minus 3, that's also 1. So this is what I was trying to point out, that many of the GCDs are going to be 1 as you take bigger fields. So that the process is quite wasteful if you calculate all the GCDs. Yes. So we have actually factored it now. So these are the two factors, and once we have two factors, that has to be irreducible. Let's just write it as this. So I just give two names for this. So let's call this F1. Uh, let's just call it F1. That is a factor of F. So get the same thing. So that we call it, just give some name. So F2, that's the second factor. So just giving name makes it easy to check the factorization. So we want to now multiply this F1 into F2 and then subtract F. So yes, so we get a 0. So we got a factorization. So if the polynomial, the 9th degree polynomial which we started with, this is the polynomial x to the 9, 4x to the 6, 3x to the 4, 3 x cube plus x plus 4 over f5 is now factored, and the irreducible factors are, so once we factor into two factors, we don't have to check, because since the null space has dimension 2, it has to have two irreducible factor. Once we factor into 2, it has to be irreducible. So they are definitely irreducible. You can again use this process to check them, check the irreducibility, but they are irreducible. They have to be irreducible. So, and this is the factorization. So the first factor is this linear factor x plus 2, and second factor is this. So I would stop with that. Sorry, I have actually overshoot the time because this matrix took long time to write. Yeah, so I'll stop. So any question? Of course, the time is short. Any question is welcome. I will also send this as a PDF file. This calculation, both the examples I would send as PDF files.
Okay, sir.
Okay,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.
Yeah, you are welcome. Yes.
Okay,
So
sir.
any question is fine.
Okay, sir. I think no questions from the audience. Let's start our validatory function.
Okay, so I'll stop sharing them.
Okay, sir.
Shall I? Yeah, so yeah.
Okay, sir. So good evening to all. On behalf of Department of Mathematics, MEPCO Engineering College, Sivagasi, I welcome you all for the validatory function of online TEW on algebra and discrete mathematics from November 19, 2020 to January 3, 2021. So first of all, I welcome Dr. S. Arivalagan, principal of our college, who motivates us to organize such workshops in our college. Welcome, sir. Then I welcome the academic convener, Professor K.N. Raghavan, sir, IMSC Chennai, who gives us constant support and guidance to organize this TW workshop in our campus a second time. Welcome, sir. Also, I welcome the honorable resource persons, Professor Anirban Mohabadia and Professor Sangaran Vishwanath from IMSC Chennai. Welcome, sir. Then I welcome the local organizer, Dr. R. Radha Jalashmi, HOD Mathematics, who is encouraging us to organize this workshop in a fruitful manner. Welcome, ma'am. Finally, I welcome all the participants from various parts of our country for this validatory function. Thank you. So now I invite Dr. S. Arivalagan, Principal, MEPCO Engineering College, to deliver a validatory address. Sir, please.
Good evening to all.
Good evening, sir.
Good evening, sir.
I'm happy to be part of this workshop, teaching enrichment workshops on mathematics. In the last day of the workshop, I'm happy that even the workshop would not be able to be conducted in a face-to-face manner as done in the last year in our campus. The entire workshops were handled well for the last around 45 days, having sessions on each day. I really thank Professor Raghavan, Professor Anirban, Shankaran Vishwanathan, and other resource persons who contributed a lot. So today morning, in one of the talk show, I noticed that actually, so during the pandemic, there is a very heavy impact on the education. When the speaker told, okay, Tamil mean unoruburomai solli kodukka vendum. English mean you can speak and you can teach English actually. Max mean you need to solve the problems. Then only you can teach actually. Yeah, social science mean you should make the students to visit places. Then only you can teach. History mean you need to teach with the proof, with the evidences. So when I'm looking at that actually, for all the teaching community, it's a very tough challenge today to deliver the topics in our own domain, in our own field, starting from one looking at our domain actually, starting from maths, physics, chemistry, English, and all related engineer subject. In some subject, it is we feel comfortable. Some subject it's very difficult. We found tough time actually, and particularly to keep the students on our tap. But despite it's a mathematics enrichment workshop on algebra and discrete mathematics, the team IMC team has really conducted the workshops very positively, spreading the earlier 2 weeks, 3 weeks workshops over 45 days with the sessions on all days actually. And also, let me congratulate the mathematics department, the Jodi Radha Jalakshmi madam, and the entire mathematics faculty team for continuously getting interested in arranging such workshops for the betterment of the faculty community, and particularly those who are teaching mathematics actually, irrespective of where they are located. Right? That's actually that's actually any aim of any objective of any minimum duty of any education institution, impart knowledge. Right? So here imparting knowledge is done by the Professor Raghavan and his team, and we are happy that actually we could able to make it as a platform. We are acting as a platform for the same actually, and our coordinators actually doing a tremendous job in coordinating all the activities with both the speakers and as well as the participant from all over the places. Despite this pandemic, despite the situation which forces us to conduct such things, right? This is conducted nicely in a successful manner. Let me congratulate each and everyone who be part of this program. Thank you. And I hope all the participants are getting benefited by participating, by enriching your knowledge in the domain. Thank you.
Thank you, sir.
Thank you, sir.
Raghavan, sir.
Good evening, everybody. I just want to thank MEPCO Engineering College, Dr. Harivaragan, for the support and for organizing this, to Dr. Radha Jalakshmi and to our Guruswami for doing a wonderful job of organization. They've worked very hard. So to the entire team, I express my thanks on behalf of the NCM. Thank you so much.
Thank you, sir. So I kindly request our participants to give their valuable feedback, which will be helpful for us to improve in future.
Good evening to all. I'm Dr. Usha, Faculty of Mathematics, MEPCO Shalank Engineering College. First of all, I would like to thank organizers for the opportunity of attending this workshop. I was greatly impressed by all these lecture sessions. One more thing, this platform makes me to know about group actions, which is new for me, as I have not studied about so far. It motivates me to learn more about the same in future. Once again, I thank academic convener, resource persons and organizers. Thank you all. Thank you.
Thank you, ma'am.
Thank you, Goswami.
Thank you.
I have a small suggestion. Maybe the people who speaking can also be on video, just so we get a better feel for what they're saying.
Good evening, sir. Good evening to all. I am R. Shankar Alias Deepa, Ajjabalayam Raju's College. First of all, I thank the organizer to conduct such a wonderful program. And all the tutorials and the lecture sections are very useful, sir. Really, I don't know about the group action, but still now I have some ideas about that, sir. And also the way of you interacting with us and way of teaching and you are explaining the concept was very useful and outstanding, sir. So also, finally, I really thank to all the such wonderful teachers, sir. Thank you, sir.
Thank you, ma'am.
Hello, everyone. Am I audible?
Yes, you are audible.
Thing is that I have a lot to say, but I am at my brother's marriage, but still I attended your sessions because it was very good program. So I just want to say that I have attended AFS 1, 2, as well as I have attended one advanced instructional school and the teachers enrichment workshop as well. But I can surely tell one thing, that this was the best program so far which I attended. So I would like to thank you all for the wonderful session.
Thank you, sir.
I would like to thank for giving this opportunity in this workshop, because this workshop has given me a great insight on algebra and discrete mathematics, and also a special mention about the tutorial sessions, because this had given me a better perspective of understanding the concepts and also a new approach to solve problems in different ways. And on the whole, it had given me a new dimension in solving problems and also to understand concept in a better way. So I would like to thank giving me an opportunity for attending this workshop, and it had given me a great insight on mathematics on the whole. Thank you.
Thank you. Am I audible, sir?
Yes, you are audible, sir.
I am Shakti Ganeshan, sir. I am from PSG College of Technology and from the Department of Applied Mathematics and Computational Sciences. First of all, I thank the selection committee for giving me the wonderful opportunity to take part in this workshop. And regarding the workshop, overall it was a nice experience of recollecting some important topics which we have studied during my postgraduate period. Especially, I enjoyed the sessions over the context of finite fields. And finally, I want to thank all the professors for carrying out all the sessions in an interactive and interesting manner. Thank you, sir.
Thank you, sir. Thank you for your valuable feedback. Okay, thank you participants for your valuable feedback. So now I welcome Professor Anirban sir to give his valuable feedback.
Yeah, so I would like to thank everyone, for all the participants for attending my lectures, which probably had been tortured at certain points, and I mean, hope you have enjoyed some part of it at least. And this, and I also like to thank the organizers, uh, mm, Dr. Guru Shami and Dr. Ataja Lakshmi for giving me this opportunity to speak. It was so nice. In fact, I would have liked to be in MAPCO College to do this, but the situation forbids that. So it's the next best option. So thanks to everyone.
Thank you, sir. Thank you so much, sir. So now I welcome Sangran Vishwanath sir to give his valuable feedback.
Yeah, I personally enjoyed lecturing this workshop a lot. I hope people got something out of it. I should say I was also a little apprehensive about how this whole online format would work on a workshop of this scale, but I think so it at least broadly, I think it all worked without any technical hitches. That's at least that was again a big worry. You know, what would happen if suddenly internet went off for long periods of time and we had power cuts and various things like that. But somehow I think we've been lucky that none of that has particularly impacted the session. Thanks especially to Guruswamy and Professor Radha for this sort of flawless organizing in some sense. Thank you very much.
Okay, sir. Thank you, sir. Thank you so much, sir. So now I welcome the academic convener, Professor Raghavan sir, to give his valuable feedback.
Thanks once again to MEPCO. I think Drs. Radhajalakshmi and Guruswamy have done a wonderful job. They have put in a lot of work. It's really thank you so much. And like Professor Anirban said, I would have liked to be in person at MEPCO, like I was there in 2019 May to conduct this workshop. But this is the next best thing. And doing things online, as Professor Vishnath said, we were apprehensive about it, but it has some advantages, one hopes. And so hopefully the lectures were, although they may have sounded strange at certain points, having to take this thing in remotely and just by staring at a screen. I hope that it was useful and you have enjoyed certain portions of it. The final thing I want to say is that mathematics, as was mentioned by Dr. Arivalagan in his address, is learned actively and not by. You need to engage with problem solving to really solve mathematics, and this is something that is that we don't emphasize in our college syllabi or education. And if this workshop has pointed that out and you are encouraged by means of this workshop to solve problems and to tell your students to solve problems and to engage with mathematics actively, think about what something means and how maybe to apply it, etc., then it would have been a success. Thanks once again to all the participants for your for patiently listening to all of us. And once again, Dr. Arivalagan sir, for the wonderful hospitality. Although this is online hospitality, but that has also been wonderful. Thank you again for that.
Thanks, Raghavan sir. Thank you. Thanks, Raghavan. Thanks, Anirban. Thanks, Sangran Vishwanathan. Thanks to everybody. Thanks, entire team.
Thank you, sir.
Thank you, sir.
Thank you so much, sir. So vote of thanks will be given by Dr. R. Radha Jalachmi, HOD Max. Ma'am, please.
Good evening to all. I deem it a great honor and privilege to propose vote of thanks on this remarkable occasion. First and foremost, I would like to express my heartfelt thanks to our program convener, Professor K. N. Raghavan sir, and all the NCM members for their kind support in organizing this TEW through online during this pandemic situation. Also, I thank Professor K. N. Raghavan sir, who devoted a lot of time and energy to make this TEW a grand success and have made this new normal a normal for each one of us. We are grateful to you, sir, for demonstrating and inculcating an in-depth understanding on group action and giving a new dimensional approach for each concept. Thank you, sir. I also wish to express our gratitude to Professor Anirban sir and Professor Viswanath sir for their elaborate and interesting results on finite fields and combinatorics. I strongly believe that the valuable lecture sessions taken by all the speakers have highly augmented our understanding and given an enriched insight on the concepts for each one of us. Special mention about the tutorial session, which has indeed given a wonderful platform for all the participants to experience a valuable interactive session with the speakers. So I would like to express my sincere gratitude to our management and principal for giving permission and encouraging us to organize such kind of workshop in our campus. Thank you very much, sir. Next, I thank all the participants for their enthusiastic participation throughout the workshop and making TEW 2020 an overwhelming success amidst this new normal. With a special mention, I thank Mr. R. Gurusamy and Mrs. Yamina Kumari, who worked with an untiring strength in making every part of TEW without any interruption, both on Zoom Meet as well as on YouTube Live, and uploaded every sessions regularly. Thank you very much. Thank you, sir. Also, I thank all my department colleagues and supporting staffs who have played a great role in conducting this TEW. Last but not the least, I thank each and every one for their effort in making this TEW a grand success. Thank you one and all. Thank you, sir.
Thank you, sir. Thank you, ma'am.
Okay.
Okay. Thank you, sir. Thank you for all.
Sir, thank you, sir. Thank you very much, sir.
Okay, thanks to the team.
Yes, sir. Thank you,
Thank
sir.
you.
Thank you,
Close
sir.
the session. Thanks, sir.
Yes,
Thanks,
sir.
Raghavan, sir. Convey our regards to all your members, actually.
Thank you so much. We look forward to being at MEPCO maybe in the future.
Fine, sir. Fine, sir. You are welcome, sir. Welcome. Thank you.
Thank you, sir. Thank you, sir. Anirban sir, Vishwanath sir, thank you so much, sir.
Thank you.
Yeah, thank you. Yeah,
Thank you, sir.
Thank you, sir.
Thank you.
Thank you all.
Sir.
Thank you.
Bye.
Bye, sir. So participants, please fill the feedback form and the evaluation form as early as possible. Thank you. Radha ma'am.